Swayam Prabha. Digital India. Educated India.
In my previous session, I had discussed regarding the simple image transformation techniques which were there. In this session, I am now going to discuss some of the orthogonal transformation that can be applied to a digital image, and thereafter some of the special indices which have been developed to identify informations other than vegetation. So, first of all, let us look at which are the major orthogonal transformation schemes that we have. These are principal component analysis and tassel cap transformation. So, let us look at what actually is principal component analysis is. Well, it has been found that different bands of multispectral data, often highly correlated, contain similar informations. For example, Landsat data MSS band 5 and 4, that is green and red, respectively have similar visual appearances, since reflectance from the same cover types are almost equal. Image transformation techniques based on complex processing of the statistical characteristics of multi-band data sets can be used to reduce this data redundancy and correlation between the bands. One such transformation is called as the principal component analysis. The objective of this transformation is to reduce the dimensionality, that is the number of bands in the data, and compress as much of the information in the original bands into fewer bands. The new bands that result from this statistical procedure are called components. This process attempts to maximize statistically the amount of information or variance from the original data into the least number of new components. As an example of the use of principal component analysis, a 7-band thematic mapper TM data set may be transformed such that the first 3 principal component may contain over 90% of the information in the original 7 bands. Interpretation and analysis of these 3 bands of data, combining them either visually or digitally, is simpler and more efficient than trying to use all the 7 original bands. Principal component analysis and other complex transformations can be used either as an enhancement technique to improve visual interpretation or to reduce the number of bands to be used as input to digital classification procedures. To perform principal component analysis, also known as Karhunen-Lewis transformation, is applied to a correlated set of multispectral data. This transformation results into an uncorrelated multispectral data that has certain ordered variance properties. The original axes of the data set may not necessarily be having the best arrangement in a multi-feature space to analyze the data in different bands. The primary object of principal component analysis is to translate and or rotate the original axes onto a new axis system such that there is no loss of information and that the data is compressed into less number of bands. Here, a pictorial view of the process has been shown here. Figure A shows a schematic representation of a 2-band data set. Figure B shows the translation of the origin of the axis to its new position as defined by mu1, mu2, which is nothing but the mean value of the data set band 1 and band 2, while figure C shows the rotation of the new axes by a degree phi to yield a new coordinate system. Well, these axis systems which will now be defined will be known as the principal component axes. Here PC1 is the first axis known as the first principal component and is located along a direction having maximum amount of variance of information. The next axis PC2 is perpendicular to the first axis PC1. In order to transform the original data set into its new axis system, transformation coefficients are derived from the covariance matrix of the original data set. Thus, this transformation is a data dependent process and hence has to be recalculated for each data set. A linear function is used to obtain the new values in the new axis system. The transformation is performed as follows. First of all, compute the covariance matrix for a n dimensional data set. Now, compute the eigenvalues of the covariance matrix and the eigenvectors for all the n bands and p components of the covariance matrices. Here we can see the process of converting the covariance matrix into its eigenvectors and eigenvalues. The eigenvalues contain important informations. For example, it is possible to determine the percentage of the total variance explained by each of the principal components as a percentage using the equation where it is eigenvalue of any component divided by the sum total of all the eigenvalues of all the components taken as a percentage. Eigenvalues E contained information regarding the total variance explained by each principal component. Generally, it is found that the first three principal components account for nearly 95 to 98% of the information content of a 6 band of TM data set excluding the thermal band. The eigenvector, that is the EV matrix, gives the correlation of each band to each component and it is used to compute the new brightness values in the component images. The table below shows an example of the principal component analysis steps. So, first matrix shows the covariance matrix and from this the eigenvalues have been computed, and what we find is that the eigenvalue of the first component has a value which is equal to 1010, whereas the second one is only 131, the third one is 37, the fourth one is 6.73, the fifth one is 3.95, the sixth one is 2.17 and the seventh one is 1.24. What we find is that the total information content is of the order of 1193.18. Against this, what we can do is now we can find out what is the percentage contribution of information in each of the components. So, we find that the first component has a percentage contribution of the original data set of the order of nearly 85%, while the second one contributes to 11%, the third one contributes to about 3%, and if we really look at all this, it virtually comes out to be about 98% of the information which is there. The rest 4 bands actually contribute to only consider 2% of the original data set, and hence what we can see now is that by adopting principal component analysis, we have merged the data set into 3 information bands without any loss of information. The reduction of the data has taken place and we have removed the redundancy which was there in the data set. Well, this data set is now a uncorrelated data set which has been derived from a highly correlated data set. The matrix below shows the eigenvectors which have been obtained from the covariance matrix, and it shows the relationship of each of the original data set to the components which is there. If one focuses to the highlighted areas, what we find is that component 1 has greater weightage of information coming from band 4 and 5, while component 2 has greater weightage coming from band 1, 2 and 3, while the third band has major contribution coming from band 4 and so on. So, what we find is that the informations from different bands have now been put into each of the new components which is there. Another thing which the user may be interested, and that is to find out what is the loading factor, and thus we can find out what is the loading factor by the relationship R, which is a relationship between the eigenvector and the eigenvalues and the information content in that particular band. And based on the information which is there, we can now find out what actually is the loading of each data set onto each of the components. We find that the first band, which has actually 85% of information, has a very good contribution coming from each of the original data sets. All the 6 data sets are providing a huge loading factor onto the first principal component, whereas the second one, which contributes to about 11, takes into account the first 3 bands of the data set, while all other components probably have very insignificant loading coming from the new data set. What we can now see or understand that a 6 band data set actually has been compressed into 2 information bands, with all the information preserved very effectively. Having done this, now we can compute the brightness value of each of the component images which is there by this particular relationship, wherein the eigenvectors of each can be multiplied by their corresponding brightness value in the corresponding band, and we take the sum of all these to generate the brightness value in this particular component image. Here in this particular slide, the first 2 principal component images can be seen, and what we can see is that the information content here is much better than any of the individual data sets that we have been seeing continuously, whereas the third and the fourth, the information content has slowly reduced drastically. Interestingly, in PC3 image, what we find is that water bodies and dry soils have been, moist soil areas have been highlighted very effectively in comparison to all other information, while 4th, 5th and 6th bands probably have very little information of significance. The next orthogonal transformation scheme that we take up is the tassel cap transformation. If we recall, PVI considers spectral variation in 2 of the 4 Landsat MSS bands and uses distance from a soil line in a 2D space as a measure of biomass or green leaf area index. Kuth and Thomas in 1976 used similar concept using all the 4 bands of Landsat MSS. Here, all the pixels representing soil fall along an axis which is oblique with respect to each pair of 4 MSS axes. A triangular region in the 4-dimensional MSS space is occupied by pixels representing vegetation in various stages of growth. The shape of the triangular region are in the form of tassel cap, and hence this transformation is known as the tassel cap transformation. This transformation is based on Gram-Schmidt's sequential orthogonalization technique that produces an orthogonal transformation of the original 4-band MSS data space into a new 4D space. The axes of this new coordinate systems are termed as brightness, greenness, yellowness and non-such. The brightness axis is associated with the variation in the soil background reflectance. The greenness axis is correlated with the variations of the vigor of the green vegetation. The yellowness axis is related to variations in the yellowness of the senescent vegetation. The non-such axis is correlated to atmospheric conditions. The tassel cap transformation has been used primarily to monitor the growth of agricultural crops at different stages by using the brightness and greenness informations. The advantage of using this transformation is that the axes provide a consistent physical based coordinate system, as these are defined a priori. Thus, any variation in crop cover and the stage of growth from image to image will not be affected. Generally, the first two indices contain most of the seen information, that is 95 to 98%. Kuth and Thomas found that nearly all 98% of the variance in the bright bare soil spectra from several different soil types could be explained by the soil brightness axes, and that a global valid soil line exists that could be applied to Landsat MSS Agricultural Sciences. Greenness is an orthogonal deviation from the mean soil line and is used as a measure of the green vegetation presence. Further the distance perpendicular to the soil line, greater is the amount of vegetation present within the field of view of a pixel. So, based on this, the four axes were defined and correlated to the four MSS bands data as being given by these equations. These are soil brightness index, which is nothing but a coefficient of 0.332 multiplied by MSS brightness 4 value plus 0.603 multiplied by MSS 5 brightness value plus 0.675 multiplied by MSS 6 brightness value plus 0.262 multiplied by MSS 7 brightness values. Similarly, the green vegetation index, the yellow vegetation index and non-such indexes have been computed. With the advent of TM data set, Christ and Secone in 1984 explained this concept for 6 bands TM data set excluding the thermal band. It was observed that the TM bands contain significant information related to the wetness in the third dimension. The figure below shows the TM tassel cap functionality between the brightness, greenness and wetness in two planes. So, if we look at the brightness and greenness axis and the third axis is the brightness axis, what we find is that the brightness and the wetness axis, it can be defined as the plane of soil, while greenness and the brightness axis, the plane defined by these two axes can be defined as the plane of the vegetation. So, if we transform and look at from the plane of soils and the plane of vegetation perpendicular to this, we find this is the zone, a transition zone which is there. The brightness information is a weighted sum of the entire 6 TM bands and is a measure of overall reflectance. It is helpful in differentiating light soils from dark soils. Greenness is the contrast between the near infrared and the visible reflectance and is a measure of presence and the density of green vegetation, while wetness is the contrast between the short wave infrared and visible or near infrared reflectance. It is a measure of the soil moisture content, vegetation density and other class characteristics. This particular figure, as a matter of fact, shows the different type approximate locations of the important classes in TM tassel cap feature space. The plane found between the brightness and the greenness is known as the plane of vegetation, while the plane found between the brightness and the wetness is known as the plane of soil. By plotting the brightness, greenness and wetness, certain specific and interesting informations are revealed. When greenness and wetness are plotted, it provides informations regarding the strong correlation of the percentage of vegetation cover. This can be seen in the next figure, wherein we can see that as the information spheres move from wetness to greenness, it is an indication of the amount of vegetation present. The distinction between the forest or natural vegetation and the cultural vegetation, cultivated vegetation, is enhanced in the wetness dimension. In the greenness brightness projection, it is found that there is a distinct separation between the cultivated vegetation and forest. The location of forest is of interest as it forms a badge of tree in front of the cap. The table here, as a matter of fact, it shows the various coefficients by which the different TM bands are to be multiplied in order to obtain the brightness, greenness, wetness, haze and fifth and sixth components in order to get the information in the new transformed axes which are there. It is interesting to note that the fourth dimension, which is the haze, as a matter of fact provides information regarding the atmospheric correction that is present at each pixel. The fifth and sixth are yet to be defined, and probably the information which is present there can be attributed to the noise of the sensor data. So, let us now look at how do we formulate the coefficients of the tassel cap. Since there are three broad features on the earth surface: vegetation, soil and water, let us consider different conditions of soil, water and vegetation. Let us consider that there are pixels related to soil surface which is dry. There are pixels which are consisting of wet surface, green vegetation and senescent vegetation, and these are represented as XD, XW, XG and XY respectively. Assume that the data is collected in n bands of, thus there will be n indices. So, the first index that will be derived is a relationship between the soil data. So, let us find the difference between dry and wet surface. So, BI, as a matter of fact, it finds out the vector between the dry and the wet soil which is there, and this is found for each of the band. Then this, on the basis of this, a normalized vector B is computed, which is nothing but the summation of the BI squared and square root of the same. Having computed the normalized vector B, the coefficient of brightness can be expressed as A1I, which is equal to BI divided by capital B. Now, the brightness at any point can be expressed as BR is equal to A11 multiplied by X1, which is the brightness value in the first band, A12 multiplied by X2, which is the brightness value in the second band of the original data set, and so on till the n bands of data, and this will yield the brightness value at every point in the image. The next indices which is to be developed is a relationship between the vegetation and the soil. So, first of all, let us find out what is the greenness vector which is there. So, what we do is we subtract the green brightness value from the soil which is dry for on each of the band, and now subject it to a Gram-Schmidt's orthogonalization sequential approach, wherein now we are going to abstract the brightness component which may be there in the information, which is represented by a factor D2I multiplied by A11. A11 is nothing but the coefficient that we have derived previously for brightness, where D2I is nothing but it is the difference of the green vegetation minus the dry soil multiplied by the coefficients of the brightness which is there, and we take the sum of this. This procedure is known as Gram-Schmidt's process. Having done this, we now find out the normalization factor G in a very similar manner as we have found out for B. Having done this, we can now compute the coefficient of greenness, which can be represented as A21, which is equal to GI divided by capital G, and thus the greenness of each point can be expressed and computed in the same manner as it has been done for brightness information. The third index is a orthogonal index with to the greenness and the brightness. So, let us first find out the difference between the yellow and the dry soil, where yi is the difference vector between the yellow and the dry soil minus the contributions which may be coming from greenness and brightness factors in this particular axis. So, now we define two coefficients D31 and D32 in the similar manner as it has been defined in the previous case when we were looking at greenness. Having done this, we can now work out what is the normalization factor y and determine the coefficients of the yellowness and find out what is the yellowness at each of the point. One thing which is to be remembered here is that in order to test the orthogonality, the first two components, the coefficients, if they are multiplied respectively, the sum total should come out to be 0 or close to 0. Now, we come to the next part, and that is the special indices which are there. Under this, we will discuss three special indices. One is the normalized difference water index, which is NDWI, normalized difference snow index NDSI, and normalized burn index NBI. So, let us discuss the first special indices, that is normalized difference water index, or in short NDWI. It is observed that the reflectance of green vegetation in the region of 0.9 to 2.5 mu meters is dominated by liquid water absorption and also weakly affected by absorption due to other biochemical components. Tucker in 1980 first suggested that in the region of 1.55 to 1.75 mu meter spectral interval of the Landsat TM band 5 may be best suited band in the 0.95 to 2.5 mu meter region for monitoring plant canopy water status from space. Reflectance from certain types of vegetation in TM band 5 increases as leaf water content decreases. A number of broad channel ratios and combination techniques using TM band 4, that is between 0.76 and 0.9 mu meters and TM band 5, have been proposed for remote sensing for plant water status. The normalized difference water indices uses two IR channels, one centered approximately at about 0.86 mu meters and the other at 1.24 mu meters, and based on this the NDVI relationship has been developed, which is nothing but similar to NDVI, wherein we take the difference of these two wavelength brightness values divided by the sum of these two wavelength values. It is found that NDVI is a measure of liquid water molecules in vegetation canopies that interact with incoming solar radiation. It is less sensitive to atmospheric scattering effects than NDVI. Laboratory based experiments show that as the leaf layers increases, the value of NDWI also increases, thus indicating that NDWI is sensitive to the total amount of water present in stacked leaves. As the information about vegetation canopies is contained in 1.24 mu meter wavelength is different from that in the red channel near 0.66 mu meters, NDWI should be considered as an independent vegetation index. Next is normalized difference snow index, that is NDSI. Snow is an important determinant of the Earth's radiation balance. Snow on the ground influences biological, chemical and geological processes. Many areas on the world rely on snow melt for irrigation and drinking water purposes, and thus monitoring of snowpacks closely throughout the winter and spring for assessment of water supply. Snow is a key component of regional and global climate, and it is vital to have an accurate and long term database established on snow extent variability. Analysis of the spectral reflectance curves of snow in the visible and near infrared regions shows that the reflectance of fresh snow in the visible region remains high, but decreases slightly as the snow begins to metamorphose. In the NIR region, the reflectance of aging snow decreases considerably as compared to fresh snow. With the onset of melting, an associated snow grain size increases and the NRI reflectance decreases. Here the same is seen in this particular graph, wherein we find that as the radius of the snowflakes increase from 0.75 millimeters to half a millimeter, the reflectance of the snow cover increases significantly in comparison to fresh snow. In the visible region of the spectrum, the snow reflectance is relatively insensitive to grain size, but sensitive to contamination by dust and soot. And in the near infrared region, snow reflectance is sensitive to snow grain size and insensitive to contamination. NDSI takes an advantage of the fact that the snow reflectance is high in the visible region, that is between 0.5 and 0.7 mu meters wavelength, and has low reflectance in the short wave infrared, that is at about 1.4 mu meters wavelength, to enable distinguishing snow from clouds and other non-snow covered conditions. NDSI is defined as the difference of the reflectance observed in a visible band such as MODIS band 4 and short wave infrared band such as MODIS band 6, divided by the sum of the two reflectances. The relationship of NDSI using Landsat TM data can be expressed as follows, that is TM band 2 minus TM band 5 divided by the sum of TM band 2 plus TM band 5. Acceptable snow cover results have been found with NDSI threshold in the range of 0.25 to 0.45. The next special indices is the normalized burn ratio or NBR. Wildfires are natural part of ecosystems and play an important role in maintaining and regenerating fire dependent ecosystems. One qualitative indicator used to assess the fire effects within burned areas is named as fire severity. The parameters used to estimate fire severity are the condition and color of the soil, amount of fuel present, resprouting of burnt plants, blackening or scorching of trees, depth of burnt in the soil, and changes in fuel moisture. Fire severity has been estimated using remotely spectral indices using single data and multiple temporal index data. One index represented as a reliable means to map fire severity is called as the normalized burn ratio, computed as the difference between the near infrared and the middle infrared reflectance divided by their sum, where the net value of NBR would range between -1 to +1. The advantage of this ratio is that many parameters related to forest and forest fires can be extracted using remote sensing multispectral data. Fire causes substantial spectral changes by consuming, vegetating, destroying leaf chlorophyll, exposing soil, charring stems, and altering both above ground and below ground moisture. Reduction of chlorophyll absorption bands lead to increased reflectance in the visible region, along with tissue damage leading to a decrease in reflectance in the near infrared region. In contrast, with a decrease in crown shadow and a decrease in canopy moisture, MIR reflectance typically increases after a fire, and the change in the NIR and MIR regions can be effectively exploited for mapping burnt regions. Here in this slide, the difference image between two multi-temporal data sets for a forest region forest area has been shown. Similarly, another difference image in the late summer has also been undertaken, wherein there may have been resprouting in terms of vegetation cover. Similarly, we can see the another difference image of a adjoining area which has been subjected to fire. On the basis of the fire severity indexes, now we can identify which are the areas which have been subjected to heavy severe fire, and the red areas show higher fire severity values, and thus these are the areas where maximum damage has taken place. The next slide shows the severity in the other catchment forest area where fire has occurred. Here in this particular slide, after undertaking the fire severity analysis, the two fires can be compared. What has been observed is that the first fire, which has a higher area of damage, probably has less fire severity, whereas the second one, which had a lower area of damage, but has higher severity incorporated. Well, with this I end this session on image transformations. In my next session, I would be taking up a new topic on image classification. Thank you.